Good morning to all. Now this session is in continuation of the second unit. In the previous session we discussed orthogonal vectors and orthogonal signals. The common property of both vectors and signals is orthogonality. Now this session is in continuation to that concept. Let us start. Let us start. Again, just in the previous class, we discussed orthogonality principle. So, two signals are said to be orthogonal, two independent signals are said to be orthogonal if they were given over a time period t1, comma t2, then between t1 t2 of integral if x1 of t multiplied by x2 of t dt equal to 0, then these two signals called orthogonality. That is the essence of the previous session. Now just look at. Now, what is orthogonal vector space? What is orthogonal vector space? For example, just look at, this is orthogonal vector space. Let us consider the three-dimensional axis, xyz axis, where it contains the vectors vx, vy, vz. These three are a set of orthogonal vectors. Individually, each vector is a unit vector. So, because of containing only three vectors, it is called a three-dimensional vector space. If it contains four vectors, it is called four-dimensional vector space, like that. If it contains n vectors, we call it as n-dimensional vector space. Now first look at the word only vector space. Vector space of which one? Three-dimensional. This is a vector space of three-dimensional. All these vectors are what? Orthogonal. That means what? You take any two vectors, Vm and Vn. These two vectors equal to 1 when m is not equal to n, equal to 0. Now it equal to 1 when m equal to n. That means what? Because of unit vector. That means what? That is v of x into v of y into v of z into v of x, all are zeros. Similarly, multiplying v of x, v of y with v of y, v of z with v of z equal to 1. Because each one represents a unit vector. So unit vector means what? Mod of Vx is equal to mod of Vy equal to mod of Vz equal to 1. So this is orthogonal vector space. In the vector space, if every two vectors satisfy this rule, we call it as orthogonal vector space. Now let us consider a orthogonal vector space of n-dimensional. An orthogonal vector space of n-dimensional. In that case, let us consider the vectors v1, v2, etc., vn. All these are orthogonal vectors. Vectors okay, but orthogonal property. Orthogonal property means what? All these vectors have to satisfy these conditions. Now, for any vector, now all can be expressed for any vector that equal to, for example, v equal to some constant into v1 plus some constant into V2, etc., some constant into Vn. At the same time, there may be some error also. This is the representation of orthogonal representation of vectors for n-dimensional. Look at the words, you have to observe very carefully. This is orthogonal representation of what kind of vectors? Orthogonal vectors. Every n-dimensional vector space can be represented in this way. This is very important. Okay, this is orthogonal vector space. This is orthogonal 3-dimensional, that is orthogonal n-dimensional. Here also you can make it. For example, then this is equal to which one? Sigma k equal to 1 to n ck vk plus ve. Simply just you can write like this. This is v. This implies that error can be written as v minus sigma k 1 to n c of k v of k. Now just look at, this is the orthogonal representation of n-dimensional vector space. Now in the same way, now just we are going to discuss orthogonal n-dimensional signal set or signal space. Now just look at, now just we are going to discuss orthogonal n-dimensional signal space. Orthogonal n-dimensional signal space. Now let us consider any three vectors, independent vectors, that is x1 of t, x2 of t and x3 of t. These three are three independent. These three vectors are called orthogonal set of vectors when you take for any two vectors xm of t and xn of t, this is equal to 0 when m is not equal to n, equal to 1 when m equal to n. This is orthogonality principle. But because of the continuous signal, here we are going for the time interval t1, t2. Just look at the formula as same as the vector space. Now just look at, this is orthogonal set of signals, okay, but orthogonal set of vectors. Orthogonality means all signals have to satisfy this principle. In this way, let us consider orthogonal. This is, for example, this is a 3-dimensional. Now just we are giving direct definition to n-dimensional. Orthogonal set of signals. Orthogonal set of signals. Let us consider a set of x1 of t, x2 of t, etc., xn of t. All these are orthogonal vectors. Orthogonal, the word is very important. Orthogonal set of vectors. This implies what happens over the interval t1 comma t2. Now these condition t1, t2, this is the condition. Now just look at here, all have to satisfy the condition is that now these are said to be orthogonal set of vectors if over the interval t1, t2, if you go for xm of t into xn of t dt, that is equal to 0 when m not equal to n, equal to 1 when m equal to n. This is a definition of 3-dimensional because we considered only 3 orthogonal vectors. This is the definition of n orthogonal set of vectors. It contains n orthogonal set of vectors x of n, whether it is 2-dimensional or 3-dimensional or 4-dimensional or n-dimensional. All have to follow the same principle. That's why this is called orthogonal set of signals. Orthogonal set of signals. Now, any signal. Now, all signals, all orthogonal signals can be expressed as, For example, x of t. X of t is some constant into x1 of t, some constant into x2 of t, some constant into x2 of t, etc., etc., some constant into xn of t plus some error signal x of t. Now just look at, all can be written as summation. So I will write there. All can be written as x of t. X of t can be written as summation k equal to 1 to n c of n xn of t plus some error of t. Error of t. Therefore, here error of signal can be written as x of t minus summation 1 to n cn, and this is k equal to 1 to n. This is equal to ck and xk of t. Now just look at, this is the representation of orthogonal n-dimensional set of signals. This is called more than two signals are there. That's why we are using the word space. So space word is to be used for 3 or more than vectors or 3 or more than signals. This is the example understanding purpose of 3 signals. This is the actual representation of n signal space. Now just look at orthogonal set of spaces. Now these are very much important. Whatever the dimensional they may be, all have to satisfy this condition. So just look at, this representation is as same as the previous representation of vector n space, vector n dimensional space. That's why there is an analogy between vectors and signals. Once you remember one representation, according to that, on that basis you can get other representation as well. So this is the representation. So now in this session, this is orthogonal. We discussed orthogonal space. We discussed orthogonal space. Space means what? Minimum it should contain greater than or 3 elements, either vectors or signals. This orthogonality space is discussed for vectors. The same orthogonality is discussed for signals. This is the signals representation. In the previous one, that was the vectors representation. That is orthogonality principle. Now that's why we were discussing the concept of analogy. Now in the next immediate session, we are going to discuss what is closed and complete signal space, what is mean square error of signals. These two are important components of signal procedures. Now I am advising students, remember this representation. How to write this one? In the previous case, how did you write? Now on the basis, now how are we writing this one? So students have to focus on this one. So no need to write this expression always, no need to write this much lengthy representation, not needed always. Simply instead of that one, simply just you can follow the short notation. Short notations are very much useful for your mathematical calculations. Now in the very next session, we are going to discuss complete and closed set of orthogonal sets. After that, mean square error. After that, we will enter into the concept of Fourier series. Thank you.